Hello everyone. Welcome to the next lecture in Theory of Computation, and in this lecture we will be seeing the formal definition of NFA or non-deterministic finite automata, and we also try to understand what means with the help of an example. Alright, so let's get started. Okay, here so we have the example of NFA, and what is that NFA? It is actually a machine that accepts the set of all strings that end with 0. And how do we know that? If we look at this, we see that on getting 0, it comes to B, which is the final state represented by double circle. So we know that it's a set of all strings that end with 0. It is accepted by this NFA. Alright, now let us just observe this NFA and try to figure out what is the difference from the DFA. So if you look carefully, you can see that there is a starting state represented by this arrow. So A is the starting state, just same like the DFA. And A on getting input 0, what happens? It could either stay on A itself or it could go to B. There are multiple next states. This was not possible in DFA. And on getting input 1, it stays in itself. And what about B? We did not mention what happens to B when it gets input 0 or 1. Is it wrong or is it incomplete? No, it is not wrong. In NFA, you can actually leave it like this. It is perfectly legal to leave a state like this without mentioning anything. That is actually means that this state does not go anywhere. Alright, which was not legal in DFA, but in case of NFA, it is perfectly legal. And this is a complete NFA. Alright, and looking at this, you can guess that it is very easy to design our NFA as compared to DFA, because in DFA we have to be very careful about sending the same state to only one next state. We should also mention clearly on getting input, whatever inputs they are, we should show what is transition from each input. But in NFA, we find that even if you leave it like this, it is complete. So it is very easy and straightforward to design a NFA. Now let us try to give the formal definition. So just like DFA, NFA also is defined using 5 tuples, which are Q, sigma, Q naught, F, and del. Using this 5 tuple, we can define our NFA. And what are these? I will write it down, just it is almost the same like DFA. Q is the set of all states. The set of all states. And sigma is the input. And Q naught is the start state or the initial state. And then F is the set of final states. And del. So we saw that this Q, sigma, Q naught, and F, it is same like the DFA that we have studied. And what about delt? Delt is a transition function that maps Q cross sigma to what? We'll try to find out what's this. I'll leave it blank here. We'll try to find out what does this transition function delt map. Alright, that is what we are going to find out. Okay, so Q, Q naught, sigma, Q naught, and F are same like the FA. I hope I don't need to explain it again. So let us just try to write down the values for this particular example. So in this particular example is Q. Q is the set of all states. So what are the set of all states here? The only state we have are state A and state B. So it is A and B. Alright, and sigma is the input. So what are the inputs we have? The inputs we have are zeros and ones. Now the inputs are 0 and 1. And Q naught is start state or the initial state. And how do we know which is start state? The state that is pointed by this arrow coming from nowhere shows that this is the start state. So the start state is A. which is also known as the initial state. And what is F? F is the set of final states. So here we only have one final state, that is B, represented by that double circle. Now, what is del? How do we find out what is del? This is what we are going to find out. Okay, so when we try to find this out, let us try to do some exercise. Let us see. Let us check for state A. State A, on getting input 0, where does it go? It goes to state A itself, and state A, on getting input 0, it also goes to state B. Alright, and let's see when state A gets input 1, what happens. When state A gets input 1, it goes to state A itself, right? And that's it for state A. And what about state B? State B, on getting input 0, where does it go? It does not go anywhere, so we represent it with phi. Alright, and what about state B, on getting input 1, where does it go? It goes again nowhere, so it is again represented by phi. So we see that given a state, when it gets a particular input, it can either go to one state or more than one state. So we see that A, on getting input 0, it went to two states, A and B. And A, on getting input 1, it went to just one state, so there are many possibilities. Let's try to figure out how many possibilities are there. Suppose for this example, A and B are there, and let's see what are the possibilities that we can get. So let's talk for one state, A. A, on getting a certain input, let's say 0 or 1, whatever it may be, and getting a certain input, it can either go to A, right? Or it can go to B, right? Or it can go to both A and B. Like here, it went to both A and B, right? So it can either go to A, it can either go to B, or it can go to both A and B. And it can also go nowhere, just like we saw that was going nowhere. So this A, on getting a certain input, it has these four possibilities. It could either go to A, B, or AB, or phi. Alright, so there are four possibilities. Now let's take another example. Let's say that we have three states. Suppose we have three states. Alright, we have three states, which are A, B, and C. Now, in this example, suppose in state A, we get a particular input. So what are the possibilities? So to which A can go? A can either go to itself, it can either go to B, or it can go to C, or it can go to A and B, right? Or it can go to A and C, or it could go to B and C, or it could go to all of them, A, B, and C. Or it could not go anywhere. It could go to 5. Okay, so we see that when there are three states, we had 8 possibilities. When we had three states, there were 8 possibilities. 1, 2, 3, 4, 5, 6, 7, 8. What about this case? This was for this example. And this example, how many states we have? We have 2 states. We have 2 states, and how many possibilities we have? 1, 2, 3, 4. 4 possibilities. So seeing this pattern, we can figure out a formula for this. We see that there are 2 states, it has 4 possibilities, and when there are 4 states, there are 8 possibilities. So we can say that it is 2 raised to power 2. This is 4. 2 raised to power 3. This is 8. So we can say that this transition function, it maps Q cross sigma to, can we guess it? Yes, I hope you have guessed it. It is 2 power Q. 2 power Q. That is 2 power the number of states. So that is what our transition function maps to. In case of DFA, it was Q cross sigma to Q, because every state, it leads to only one next state. But in this, every state can lead to multiple next state, and it has 2 power Q possibilities to choose from where it can go and getting a particular input. Alright, so that was the formal definitions that we could give to our NFA. It is defined using 5 tuples Q, sigma, Q naught, F, and del, while Q, sigma, Q naught, and F the same as DFA, and only different thing is transition function del which maps Q cross sigma to 2 power Q. So I hope this made the formal definition of NFA clear to us. So in the next lecture, we will be explaining about this particular example in a more detailed way which will make it more clear to us. Thank you for watching.